Now let us find out the shear force diagram and the bending moment diagram of a simply supported beam which is loaded with a uniformly distributed load W kilonewton per meter. So the first thing is we have to find out the value of the reactions. So the first equation when we balance the vertical forces is Ra plus Rb is equal to the total load, which is W multiplied by L, and when we take the moment, so moment will be Wl is the total load which is acting at L by 2, and this moment is going down, and this is equal to Rb multiplied by L. So this L cancels off. Rb is equal to Wl by 2, and when you put Rb here, you will get the value of Ra, which is also equal to Wl by 2 kilonewton. So we have got the values of Ra and Rb, which is Wl by 2, and here also it is Wl by 2. So I am going to rub this. Now we will find out the shear force. So first of all, I will draw a section X, and which is at a distance of small x from the end B. So I am going to write down the general equation for the shear force. So Fx is equal to, on the right side of this section, the force is uniformly distributed load, and this is W kilonewton per meter. It is distributed over a length of x. So the total force is W into x, and this force is going down, so it will be taken as positive. And the second force is the reaction, which is going up. So it is Rb. So if we want to find out at B, what is the value of x at B? It is equal to 0. So Fb is equal to, this becomes 0. So this is minus Rb, and Rb is Wl by 2. So this is minus Wl by 2. At A, what is the value of x? X is equal to L at x at point A. So F A is equal to small w multiplied by L minus Rb. Rb is Wl by 2. So this comes out to be positive Wl by 2. Now we have got the value of the shear force at point B as well as at point A. Now we'll go for the bending moment. So the general equation for the bending moment will be the force, the uniformly distributed load on the right side is W into x. So this load W into x will take the beam down. So it is a case of hogging, and this W into x is acting at a distance of x by 2 from the section. It will act here. This is W into x, and this distance is x by 2. The other force is a reaction which is going up, so it will give a positive bending moment. So this is Wl by 2 is Rb multiplied by x. So now at B, the value of x is 0. So MB is equal to, what is the value of MB? It will be equal to 0. And at A, x is equal to L. So this also be equal to 0. Now what is happening in between? What is happening in between? This is important. So first of all, let us draw the SFD, shear force diagram. Now if I draw the shear force diagram, there is one very important point. At A, this is point B. What is the value of shear force at B? It is minus WL by 2. So this is WL by 2 and it is negative. At A, it is positive. This is WL by 2 positive. No, now I have to, the power of x, it will be a straight line. Yes, so we will just draw this. So this is negative and this is positive. In between, somewhere, we are seeing that the shear force is coming out to be 0. Shear force is coming out to be 0. And at the same point, there will be the maximum value of the bending moment. So it is coming out to be 0 at L by 2. So let us see what is the shear force at x is equal to L by 2. So it is, if we put x is equal to L by 2 in this equation, so W multiplied by L by 2 minus RB is WL by 2. So this is coming out to be 0. So at x is equal to L by 2, shear force is coming out to be 0. So at this point we will have the maximum bending moment. So let us calculate at x is equal to L by 2, what is the value of the bending moment. So this is minus W by 2 L square upon 4 plus W L upon 2 multiplied by L by 2. So this is minus W L square upon 8 plus WL square upon 4. So this is coming out to be WL square upon 8. So if we draw the bending moment diagram, so at end A and at end B, bending moment is 0, and at point C, the bending moment will be maximum. Let us calculate the value of the reactions first. So we will balance the vertical forces. RA plus RB is equal to the total load, which is equal to 1 by 2 multiplied by span of the beam multiplied by the height. So this is WL by 2. We can also represent this in this way also. The area of the triangle ADC, area of the triangle which represents this uniformly varying load ADC, this is equal to 1 by 2 multiplied by L by 2 multiplied by W. So this is WL by 4, which will be shown here. This point is C, this point is A, this point is B. So this is WL by 4, and this distance is, this is 2 by 3 of L by 2, and this is 1 by 3 of L by 2. And similarly, we will have this load here, WL by 4, it will also be same. So this distance is 1 by 3 of L by 2, and this will be 2 by 3 of L by 2. So we will take moment about point A. So WL by 4, this is the first force, WL by 4 multiplied by the distance. This is equal to L by 3. So it will be a clockwise movement. Another force is this one, WL by 4 multiplied by, so this is L by 2 plus L by 6, and this is equal to the anti-clockwise moment, which is RB multiplied by L. Now when we solve this, so this L and this L cancels off, so RB is equal to WL upon 12 plus WL upon 4 1 by, so let us say this is 6 and this is 3 plus 1, this is equal to, this is RB. So WL by 12 plus WL by 6, and this will be equal to WL by 4. So RB is coming out to be WL by 4. So when we put RB here, we will get WL by 4. So RA is equal to RB is equal to WL by 4. Now I am going to rub this. So we have got the values of the reactions. Here it is WL by 4 and this is also equal to WL by 4. Now we have to find out the rate of loading. So let us take a section X and this distance from the end A is X. Now here the rate of loading is W. We have to find out the rate of loading at the section. So this is W, this distance is L by 2, this is our section XX, this rate of loading we have to calculate, and this distance is small x. So rate of loading upon X is equal to W upon L by 2. So rate of loading at the section is coming out to be 2W X upon L. So now let us write down the shear force equation, the general equation for the shear force. Fx is equal to, so we will consider the forces on the left of the section. So this area of the triangle will give us the force. So the area of the triangle is 1 by 2 multiplied by x multiplied by the rate of loading, which is 2Wx upon L. So, and this force which is on the left of the section is going down. So it has to be considered as negative. Another force is the reaction RA, which is going up. So it has to be taken as positive. And now this 2 cancels off. So this is RA minus WX square upon L. Now as you are seeing, the power of X is 2. So the shear force variation which we will show on the diagram will be shown by a parabolic curve. What is the value of RA? So RA is WL by 4 minus WX square upon L. So at point A, the value of X is 0. So this shear force at A is equal to, this becomes 0. So it is WL by 4 kilonewton. At point C, the value of X is L by 2. So F at C is equal to WL by 4 minus W upon L multiplied by L square upon 4. So L and L cancels off and you get a value of 0. So at C, the shear force is equal to 0. Now we will write down these values at both the points. We have calculated the value of the shear force at X is equal to 0, that is at point A, Fa is equal to WL by 4, and at C, X is equal to L by 2 and Fc is equal to 0. In a similar fashion, if we move from this side and consider a section XX and the distance from end B is X, we will get the similar values. But there will be a difference. Here we are getting a positive value of W, but here we will get a negative value of the shear force. So we will just draw the shear force diagram. I am going to draw this. At A, it is equal to WL by 4 and it is positive. So I have drawn WL by 4. This is point A, this is point C, and this is point B. Now the curve has to be a parabolic curve. So I will draw it like this. And when we move from this side, suppose we start from this side, so the diagram which we will get will be of, it will also be a parabolic curve, but the value of the shear force at point B will be WL by 4, but it will be negative in nature, and here it is positive. Now we will draw the bending moment diagram. So Mx is equal to, we have to consider the force this, and because of this force, this uniformly varying load, the moment this will take the beam downwards, so it will be a case of hogging. So we have to put down a negative sign. Area of the triangle is 1 by 2 multiplied by x multiplied by the rate of loading 2Wx upon L, and this is basically acting at a point 1 by 3 of x. 1 by 3 of x, because this will act somewhere here, and this distance is 1 by 3 of x. So this is the bending moment due to the uniformly varying load. Then the next one is RB, which is going up, so it will be case of sagging. So this is RB multiplied by x. So this 2 and 2 cancels off. So this is minus Wx cube upon 3L plus the value of RB is WL by 4, WL by 4 multiplied by x. So here we are seeing that the power of x is 3, so it will be a cubic variation. You have to show the variation of bending moment by using a cubic curve. So at B, the value of x is 0, so MB is 0, and at C, the value of x is L by 2, so MC will be equal to, you have to put L by 2 here, minus W upon 3L, so this is L cube upon 8 plus WL upon 4 multiplied by 2. Now this will be equal to minus WL square upon 24 plus WL square upon 8. So it is coming out to be WL square by 12. So now we are going to rub this and we will draw the bending moment diagram. As you have seen at point B, this is A, this point is C, and this point is B. The bending moment at B is 0, and the bending moment as at C is WL square upon 12.